Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. Okay, the date for today is September 14, 2024, and the time is 11:55. It's almost 12 o'clock. Okay, my topic for this evening will be it's actually a DC circuit, and this will now be lesson number 18. This is a long video format. Okay, so this is a continuation of my long DC format DC circuit, and the title of the topic for tonight will be I am on the topic superposition theorem. For tonight, I will be solving the problem that was solved by superposition and evidence. And for tonight, I will be solving that same problem by using the Norton's theorem. So this is actually the so-called fact checking. Okay, we are checking the validity of the answer from the solution of the superposition in Norton's, and let's try to see if the answer will still be the same by using Norton's theorem. Okay, let's proceed. The subject matter for tonight will be DC circuit, lesson number 18. And the title of the topic, we are on the topic superposition, but we are fact checking the solution of the superposition in Thevenin's theorem. For tonight, we will be using the so-called Norton's theorem. So the title of the topic will be Superposition Theorem versus Norton's theorem. This Norton's theorem will fact check the solution of the superposition theorem from previous lesson number 16, I think. Okay, let's try to bring out the figure. The figure will still be the same circuit parameters and values. So we've got a DC circuit, two voltage sources, 24 volts and 12 volts. They are connected in parallel. We got a resistance here of 4 ohms. And this is 6 ohms. And the connected load at the middle is actually 12 ohms. So it seems R sub L is 12 volts. The problem is just asking what will be the current passing through this 12 ohm load here by using Norton's theorem. Okay, we are done with the so-called superposition theorem and Thevenin's theorem. That was actually lesson number 16 and 17. So I place it here. By using the same problem, the current passing through the 12 ohm load by using the superposition is 1.34 amperes. Lesson number 17, we solve again the same problem by using Thevenin's solution theorem. Okay, so the second solution is actually Thevenin's. Same problem. The current is still 1.34 amperes. So for tonight, we will be solving the same problem by using Norton's. And let us try to see if this current here still will come out to be 1.34 amperes. I think the final answer here, if we try to go back to this part end here, the current passing through the 12 ohm load is actually 1.34 amperes. It's 12 AM. Okay, I will try to shut off my alarm. Okay, the final answer here, we'll go back to the first part later. The current passing through the 12 ohm load is actually 1.34 amperes. So actually, the third solution for tonight, the so-called Norton's, okay, the current is still 1.34 amperes. Okay, let's try to bring out the solution by using Norton's. The previous concept of Norton's, we are just solving a current when the voltage source and the circuit is just one. But for tonight, it is a little bit complicated because we got two voltage sources. Okay, that's why our original topic was superposition, and superposition theorem is actually being used for voltage circuit or for circuits in which the voltage source is actually more than 1. Okay? So for tonight, it will be 24 volts and 24 volts. Okay, let's try to bring out the solution. The problem is just asking what will be the current passing through this 12 ohm load here using Norton's theorem. That's our third solution. Okay? It's a little bit complicated. We got 2 voltage sources. Okay? Let's try to bring out the solution. Step number 1. There are actually 3 steps. For Norton's step number 1, we'll try to disconnect the 12 ohm load. We'll try to disconnect it. Short the terminals with short. Okay? And solve for the capital letter I with the subscript AC, meaning the short circuit current. So for step number 1, there are 3 things to be done. We disconnect the load, we short the terminals, then by using our knowledge of the theoretical solution and how to compute for the short circuit current, we will solve for capital letter I with the subscript AC, meaning the short circuit current. That's step number 1. So for step number 1, let's try to bring out the figure. For step number 1, like what I said, disconnect the load. We disconnect the load. We remove this one. Okay? We remove it. That's step number 1. But according to step number 1, then short the terminals. We short it out. We put a shorting wire. So this could be terminal A, terminal B. And on step number 1, the third procedure is solve for I short circuit. So if we try to short the terminals, meaning short the terminals, we assume that the resistance of the connecting wire will be 0. We will solve for I, capital letter I with the subscript AC, meaning the short circuit current. If we try to disconnect the 12 ohm load, we short the terminals, what will be the value of the short circuit current? Okay? If we try to bring out the value of the short circuit current, we will be using the so-called Kirchhoff's voltage law. So I place it here. The current coming from the 24 volt source when this is shorted is I sub 1. And the current coming from the 12 volt source when this is shorted is actually I sub 2. So to compute for the short circuit current, okay, we must have to compute for I sub 1 and I sub 2. And to compute for I sub 1, we will take the so-called Kirchhoff's voltage law. So I place it here. Consider the left loop. Left loop is this one. Right? That's the left loop. So for the meantime, we take the summation of voltages and they should be equal to 0. Considering the left loop, forget the right loop for the meantime. Okay? So if we try to take the summation of the voltages, this is a minus to plus, that's plus 24. It's a voltage source. There is a voltage drop here. Okay? The voltage drop here should be the current passing I1, and which we do not know for the value of that one for the meantime, times 4. Okay? And this will now be equal to 0. Why equal to 0? Because there is no more voltage drop here. There is no more voltage drop here. So if we try to take the summation of the voltages, it will just be simply this voltage source here minus the voltage drop. Okay? Because we assume that the resistance of the connecting wire is 0. So there will be no voltage drop here. There will be no voltage drop here. So considering the left loop, it will just be simply 2 terms. A plus 24 minus I sub 1 multiplied by 4, and this should be equal to 0. This is now algebra. We are now given a linear equation in which the only unknown is I sub 1. If we are on algebra, that will be x. But since we are on circuitry, this will be I sub 1. Okay? One linear equation, one unknown, we could compute for I sub 1. So this will now be by applying our knowledge of so-called algebraic manipulation, right? So I sub 1, right? We transpose this to the right, so it will become plus. Then we try to rearrange. So I sub 1 now will be 24 divided by 4, and that will be 6 amperes. So the value of this one here is 6 amperes. When this terminal here is shorted, the current that will be coming from the 24 volt source is 6 amperes. Consider the right loop. If we try to consider the right loop, the configuration will be something like this. Right? And while we are taking the summation of the voltages, forget the left loop. We are done with the left loop. So this is plus 12. So this is plus 12. Voltage source. Minus the drop here. There should be an arrow. Minus the drop here. If there is a resistance here, there should be voltage drop, but we assume that the connecting wire has a zero resistance. So this is now equal to 0. Right? There are only two things to be added on the right loop, because we assume that the resistance of the connecting wire is 0. So this is plus 12 minus the voltage drop here, and the voltage drop here will be the unknown current I sub 2 multiplied by 6. So this is actually I sub 2 multiplied by 6, and this should be equal to 0. Again, we are given a linear equation in which the unknown is just only 1, it is only I sub 2. So by using our knowledge of the so-called algebraic manipulation, this is now algebra. Okay, I sub 2 now, we transpose this to the right, it will now be plus, and we compute for I sub 2. I sub 2 will be 12 divided by 6, and that will be 2 amperes. So meaning to say, when terminals A and B is shorted, the current that will be coming from the 12 volt source, whether we like it or not, should be 2 amperes. Okay? If there is a shorting wire here, this 6 amperes will not go through this 6 ohm load. Why? Because there is no resistance here. A current will pass through a path in which the value of the resistance is actually lesser than the resistance it will be passing through. Since there is a 6 ohm load here, okay, this 6 amperes will not pass through the 6 ohm load. It will just pass through the shorting wire. Okay? So, to compute for the short circuit current, right? Take the summation of the current here, considering junction A. We are using Kirchhoff's current law. Okay? Considering a junction, Kirchhoff's current law, current entering should be equal to current leaving. Okay? The current leaving is I short circuit. The current entering is I sub 1 and I sub 2. Meaning to say, this short circuit current which is going out should be equal to the current entering this junction. So I place it here, short circuit current will be I sub 1 plus I sub 2. And this will be 6 plus 2, and that will be 8 amperes. Okay? So in here, if we try to short the terminals, the total current passing through the short circuit will be 8 amperes. I need to replace my pen now. 8 amperes. Right? So we will use this one in the final computation of the current passing through the 12 ohm load. Okay, step number 2. Step number 2, we open the terminals. Okay, short the voltage sources and solve for capital letter R with the subscript N, meaning we will solve for the open circuit voltage, or the so-called Norton's open circuit voltage. So actually for step number 2, there are 3 things to be done also. Right? Open the terminals. We open it. We remove the short. Right? Then we try to short out the voltage sources. We short it out. Okay? So if we try to short it out, this will be gone, and this will be gone, right? This is now open. So what will come out will be just something like this. We short out voltage source number 1, we short out voltage source number 2, we open terminals, we will be getting or solving for the value of R sub n, the open circuit Norton's voltage. So I place it here, the value across the terminal should be R sub n. We open it. We use our tester to compute for the so-called, it seems we are having a multi-tester, then we'll place it here. Okay? That's in the actual thing, but theoretically, if we are solving on the board, okay, what will be the value of R sub n? Right? But in actuality, you just get your voltmeter and place it here after shorting the voltage source. Okay? If we try to inspect this 4 ohm load here and 6 ohm, they are in parallel. The current passing here is different from here, so they are in parallel. And since there are only 2 volt, what you call this resistances in parallel, it will just be simply the product all over the sum. That's the formula. So the product all over the sum, 4 times 6, all over 4 plus 6, or this should be 2.4 ohms. Okay, so this is 2.4 ohms. Okay, step number 3 for Norton's theorem. Draw the Norton's equivalent circuit and reconnect the 12 ohm load. Okay, the Norton's equivalent is that since Norton is a constant current source, we discussed that from the concept. If we try to draw the Norton's equivalent, the short circuit current should be in parallel with R sub n. So in here, we got the voltage source in which the value will be 8 amperes. And this should be in parallel with the open circuit voltage, which is 2.4 ohms. That is for Norton's. Right? It was different from Thevenin's because from Thevenin's, the open circuit voltage is in series with the Thevenin's open circuit voltage. But for Norton's, the short circuit current is actually in parallel with the open circuit voltage R sub n. So this will be the equivalent of it in terms of Norton's equivalent. Then we'll try, this is actually terminal A, this is terminal B, okay? And reconnect the 12 ohm load. This is the 12 ohm load, this one. We'll try to reconnect it again. So if we try to reconnect, this will be the total configuration now. And the only missing here now is actually the current passing through the 12 ohm load. Right? And as was derived from the concept of Norton's theorem, this is actually the current or the formula on how to compute. We could derive this one by equating the voltage here and here, and if we try to simplify, then compute for I-12 ohm. I-12 ohm will be the short circuit current, the one we computed in step number 1, multiplied by R sub n, the value computed in step number 2. Okay? All over the sum of the open circuit voltage plus the load RL. All values are computed, right? Short circuit current from step number 1 is 8 amperes. R sub n is 2.4. All over 2.4 plus 12. 2.4 times 8 is actually 19.2. Right? 19.2. All over 14.4. And this will be 1.34 amperes. Let's try to check it. 19.2 divided by 14.4. The answer is 1.333, or if we try to truncate this long thing here, it will be approximately 1.34 amperes. So the current passing through the 12 ohm load by using the Norton's theorem, it is 1.34 amperes. Okay, that's it, guys. So actually, lesson number 18, we just fact check lesson number 16. Okay, because lesson 16 is superposition. We use the theorem, superposition theorem, and we came out with 1.34 amperes. And we fact check the superposition answer by using Thevenin's theorem from lesson number 17. It is still 1.34 amperes. And again, we fact check this Thevenin's theorem solution. Okay, and so with the superposition by using Norton's. And again, for tonight, it came out that the answer is 1.34 amperes. So it is still 1.34 amperes. So this is fact checking, right? What they call this? We are just checking the validity of the answer by presenting another solution. So actually, we have presented two solutions here. Instead of superposition, we check it by using Thevenin's and Norton's, and the answer is still 1.34 amperes. Okay, that's it. This is Professor David J. De Los Reyes. Okay, good evening from Los Angeles. Good morning.